last theorem for 10.4 is the inscribed quadrilateral theorem. And the inscribed quadrilateral theorem states if you have a quadrilateral inscribed in a circle, then the opposite angles have to be supplementary. And then here's why. So a pair of opposite angles in this diagram, we'll concentrate on angles D and B. Those are opposite angles. Yes, A and C are also opposite angles, but I'm just going to concentrate on angles D and B right now. So angle D is an inscribed angle. Here's the arc that it intercepts, and arc ABC. And then for the opposite angle, angle B, here's the arc that angle B intercepts, which is also an inscribed angle, arc ADC. So the sum of the arcs in red, ABC, and green, ADC, that make up the full circle. So the sum of the arcs would be 360 degrees, and then angles ADC and angle ABC are the two inscribed angles that intercept each of those arcs. So they would be half the measure of each of those arcs. If you just take half of 360 degrees, that's 180 degrees. So angles D and angle B, a pair of opposite angles of the inscribed quadrilateral, have to add up to be 180 degrees. And then by definition, they're supplementary. I could have done almost the exact same thing with angles A and C. It's the same concept, so I'm actually not going to do it for both of the pairs of opposite angles of the inscribed quadrilateral. And here's theorem 10.13, the inscribed quadrilateral theorem, written out. It's written as a biconditional statement, so it can go both ways. Now we'll try to apply the theorems from 10.4 to be able to solve problems. Kind of as usual, maybe pause the video, write down the problems, and see if you can work through 1 through 5 before we go over them together. And like I usually do, besides just going through each of the questions one by one, I'm first going to take a look at the diagram and then see what we can find in the diagram and then answer some of the questions. So I know angle B or angle ABC is an inscribed angle. Yeah, it's also true that triangle ABC is an inscribed triangle, but angle B is an inscribed angle. It intercepts arc AC. So the inscribed angle is half the measure of the intercepted arc. You can take 28 degrees, multiply by 2 to get 56 degrees for arc AC. And then CB is a chord that goes through the center of the circle, N. So it's a diameter. That means angle CAB has to be a right angle. The inscribed triangle is a right triangle. So that's 90 degrees. And then you could find the measure of angle C by adding up 90 and 28 and then subtracting from 180. So angle C or angle ACB is the complement of 28 degrees. So you could also do 90 minus 28. So angle C would be 62 degrees. Angle C is an inscribed angle, so it intercepts arc AB. Arc AB would be twice the measure of that. So arc AB, 2 times 62, 124 degrees for arc AB. And then arc CB, let me get a different color here, would be a semicircle since CB is a diameter, or it's also twice the measure of angle CAB, the inscribed angle, so it would be 180 degrees. Let's see if we can answer all the questions from everything that I just filled out there. We could actually also find CB, because I noticed that's question number 3. This is a right triangle, so we could find side CB using the Pythagorean theorem. 3.9 squared plus 7.3 squared is equal to CB squared. And I'm going to use my calculator in order to figure out those numbers. So using the Pythagorean theorem, I think you could follow my steps. CB is about 8.3 if you're rounding to the nearest tenth. Okay, now let's see if we can fill out all the missing information. Measure of angle A, I have that right here. It's 90 degrees. The measure of angle C, if you can read that, it's 62 degrees. We just found side length CB or BC. It's about 8.3. The measure of arc AC right here in blue, 56 degrees. And then last, the measure of arc AB has to be that minor arc. You can't go A to B here. Otherwise, it would be named something like arc ACB. But the measure of arc AB, kind of in the maroonish color, 124 degrees for 1 through 5.